Okay, guys. So we are going to continue. Okay, with what we have been doing. So last time's topic that I gave you for some numericals I gave you. No, can you just share with me like all of you, have you tried or there was some problem in doing them? Yes, yes. You want to share? You can talk to me. Yes, yes. Some response, then I'll proceed.
So I could not do question number 5.
You could not do question number 5. Yeah, you told me no. Yes, yes, yes. You told me no about question number 5. Okay. What about others? Lilu has tried. Okay. What about others? Yeah, others are quiet. They have not tried.
Sir, I did not do because my tests are going, sir.
Okay, okay. So, okay, for you also, fine. What about others?
Yes, so I'm having exams.
You're having exams. Okay, fine. Anyone who's not having exam just did not do because very lazy. Who's that guy? Who's that student? Anyone?
I have a exam, sir.
Ex- Exam. Okay, fine. Ryan doesn't have any exam. What about Ryan? Yes, yes, Ryan. What excuse Ryan has? Yes. So you did or not? You did not do. You did. Ryan has done it. Oh, good, good, good. Ryan has done. Very good. Okay. Okay, so we are going to move ahead. Today's topic is going to be very difficult. Okay, I'll do only one topic. I already told you it's going to be difficult because of something called integration we are going to bring. Okay, I'll try my best to still talk about that. Okay, the topic. Uh, I'm going to go slow. Okay, I'm not going to be in a hurry. And whatever you can learn from that, okay, I'll be fine with that. Okay, so just check how we are. I'm going to do the things and all. You check all the steps. Okay, I'll maybe teaching you slowly. Okay, but I will do it properly. And in between, you have to stop me if you have any doubts. Okay, please feel free to do that. Huh? So I'm going to start right now without wasting any time. But this topic you have to learn properly. Huh? So say, uh, okay, let's start. Okay, so I'll just write the heading first, then we'll proceed. Okay, so say we are talking about escape velocity today. Okay, 1 second, 1 second. Just give me 1 second, guys. Okay, this is what we are going to do. Okay, escape velocity we call it. Very important topic. They ask you derivation or maybe numericals. We can call it escape speed also. Okay, so any one of them you can just check. Any one of them we can use. Okay, so let me just start with the theory first. What is it? And then we'll proceed. Okay, see, suppose I'm taking a planet. Let it be any planet. Let's start with Earth. This is the center of the Earth. All of you know this is the radius of the Earth. All of you know, right? Radius of the Earth is RE. We have been taking mass of the Earth. We have taken to be ME. That's the mass of the Earth. Right now we have an object which has a mass of m and it is present on the surface, right? This object of mass m is on the surface of Earth. Okay, I want to take this object that is present on the surface of the Earth. Let it be any object. Okay, I'm just taking this object, but actually we are talking about any object. Okay, I want to take this object, throw it with some velocity. Throw it means just send it, no, just throw it upwards. Okay, against gravity we're going to throw it and throw it and throw it, okay, with some velocity, and I want it to reach very far. When I say very far, it means really very, very far. Okay, we call that position as infinite distance, right? We call it infinity also. The point is called infinity. We want to send it to a point which I'm going to call infinity. I'll tell you the property. Infinity means, of course, right, is so and so very far point. Okay, very far point you cannot even imagine. I want it to send it there. Okay, and why I want to send it there? Because if the mass reaches here, okay, I'm repeating again, if the mass reaches here, the distance between the mass and the earth will be so big. Okay, this is the distance. See, let me show you. This will be the distance between the mass and the earth. Okay, and this distance will be called infinite distance. If the object is at infinity, right, the distance between the earth and the object will be not infinity, sorry, infinite distance. Okay, infinite. I told you I'm going to go slow, so please bear with me. Infinite distance between what and what? Between earth and the object that we're talking about. Right? So I want to take it so far. Okay, now what will be the advantage? Let me tell you, or not advantage, let me tell you what will happen. See, this is an object of mass m, this is earth of mass me. The gravitational force, let me just quickly calculate. Okay, the gravitational force will be equal to this much. See, capital G, mass of the earth, object mass is small m, the distance between them, right, if I take it to infinity, the distance between them, okay, because the object is no longer here. See, I've sent it so far from the surface of the earth, it is so far that the distance is infinite. No, so after a distance square, I told you just now, the distance is infinite, so infinite we write a symbol like that. No, infinite. Okay, infinite square. It's such a large distance, that's why I'm not writing it any number here, I'm calling it infinite square. Okay, that's how we are going to write a very large distance. No, this automatically is going to give me 0. Why? Because we are dividing this whole term by a very large number. Whenever I divide something by a very large number, right, I'm surely going to get a number which is very tiny, very small, almost equal to 0. Okay, that means if I ask you now, what is the force of attraction, what is the force of attraction between the mass and the earth right now, the mass is present at infinite distance, you have to say that the force of attraction is 0, and this object will never fall to earth, no chance, because there's no force of attraction, right, because it's so far, so the object is not going to come back to earth. Okay, we say that this object has escaped, not as this one, escaped. Okay, we say that the object has escaped the gravitational pull of the earth. I hope it's making sense, no, because it's so far, the force is calculated, found to be 0. The object, I will say, has escaped gravitational pull of the earth. Another way I can say, the object has escaped earth also, we can call it, we can talk like that. Okay, so now check. I'm going to show you something and I think you will be clear what am I talking about. Okay, I think till now it's clear, right, guys, I think you understand what I'm saying, right? I'm trying to send the object so far that it doesn't fall back to earth. I have to really send it so far that the force becomes 0. I have to send it by a distance called infinite distance. Okay, very far. Okay, okay, now check. Let's try to do this now. Okay, if you have doubts you can stop me, huh? So now see, let's try to do it. Okay, so let's really try to send it. Okay, I take the object, throw it away from earth upwards. Okay, just like throwing a rocket, but I throw it up with a small velocity, let's say only 10 meters per second, or let's say let's increase, no, let's say only 100 meters per second. You must have done this. Okay, you take a cricket ball and throw it on the air, no, so you must have done that. Let's say the velocity is 100 meters per second. Okay, you tell me, will the ball uh, fall back to earth or not? Simple question. You are throwing it. Okay, you are throwing it, you're really holding a ball, throwing it in the sky. Will the ball fall back to earth or will never fall back to earth, or will it just go away from earth? Simple question. Yes,
Fall
yes,
back, sir.
yes, yes. It will fall back, right?
Fall back, sir.
It will fall back. Yes, very good. Okay. Obviously, it's going to fall back. Okay, let me show you the path also. Because you have sent it with a velocity, let's say 100 meters per second, the path will be like this. Go up, but again fall back. See. So you tell me, did the object escape the gravitational pull or did not escape? The question is, did the object escape the gravitational pull or did not escape? What do you think? The earth is still pulling it, or let me ask you like this. Did the object reach infinite distance or did not reach the infinite distance?
Did not reach, sir.
Okay, did not reach infinite distance. Okay.
Did
Okay.
not reach the infinite distance.
Oh, did not reach infinite distance. Okay, fine. Okay, now check. The speed was only 100 meters per second. Okay. What will happen if I try to throw it much higher velocity? Much higher velocity, not 100. Okay, let's say 1000. 1000 meters per second. What will happen now? Will it go high or much higher now? It will go much higher, right? It's common sense. It will go much higher because a much larger velocity, the object is going to go much higher. But you will notice again the object is falling back. Okay, I'm exactly telling you. Okay, it's the correct number, huh? So the object is still okay, though you tried not 10 times faster, right? This object is set 10 times faster, but this object still finds. But you find that the object still comes back to the Earth. Okay, okay. Then see, I'm going to do something. Okay, I'm going to still let's throw with much higher velocity. Let me change the unit also. Okay, let's say that 1000 meter per second was like 1 kilometer per second. Okay, 1 kilometer per second. Just now I showed you, know. Let's make it 5 kilometer per second. If I throw it with a speed of 5 kilometer per second, okay, the speed is much larger now, 5 times more than 1 kilometer per second. You will notice the object will still go much high. Okay, but you will notice the object still does not reach infinite distance. Okay, it doesn't reach. That means there's still force when the object reaches here. No, now it has lost the speed because of deceleration due to gravity, and the object is still going to fall to Earth. Please remember this. Okay. Now let me show you something. Say, if, however, okay, if you are throwing this object against gravity with a speed, okay, with a speed of 11.2 kilometers per second, very high speed, you will notice that this object, okay, doesn't matter what is the mass of the object, this object is surely going to reach where? It's surely going to, not surely, let's say it is going to reach infinity. That means very far from the Earth, so that even the Earth cannot pull it back. That means I have to say that object has escaped the gravitational pull of the Earth. And this happens when you throw or project the object vertically away from the Earth, right? Okay, don't throw it horizontally, okay, throw it vertically away from the Earth. It is going to reach infinite distance, and it is, I'm going to say that the object escaped the gravitational pull of the Earth, okay? And of course, right, even if I throw it 14.5 or let's say more than 11.2, right, 11.3 also I can call it. Even if I throw it 11.3 kilometer per second, obviously it's much higher speed. Obviously, it's going to reach infinity. Okay, it's going to escape the gravitational pull of the Earth. Okay, but the minimum required is how much? The minimum velocity with which you should project this object such that this object will never fall back to Earth, or let's say it will be escaping the gravitational pull of the Earth. The minimum value of the velocity required to do that, required to send the object to infinity, right? We call it escape velocity of this planet, let's say Earth. Okay, right now I'm talking about Earth. So this is the escape velocity of Earth. Are you getting me? What is the meaning of escape velocity? It is the minimum velocity with which if a body is projected, right? With which if a body is projected, is surely going to make the body escape, okay? Escape gravitational pull of the Earth. And the object will never fall back to Earth again, okay? And we have come, okay, I've written the numbers already. I'm going to show you that the numbers comes out to be like that. But I think you got my point, right? Okay, now I'm going to go to some different planets. See, let me quickly ask you that. Okay, let's take, this is Earth, let's take Jupiter. Jupiter is very big. If I ask you mass of the Jupiter mj, radius of Jupiter rj, and let's try to do the same thing. Let's try to send this mass or some object away from Jupiter such that it doesn't fall back to Jupiter. Okay, I want to send this object again to where? Again to infinity, very far. My question is 11.2 kilometer per second. If I throw it up with this much velocity, what do you think is going to be enough or not enough for this object to escape gravity from Jupiter? What do you think? That is my question. What do you think?
Not enough, sir.
Yes, it is not going to be enough. Let me tell you why. Because the force between this mass m and Jupiter, right? The force between them, the force of attraction, the gravitational force is going to be very high compared to Earth and that mass. That's why if the object can escape with a minimum velocity that is 11.2 from Earth, the same object cannot escape from Jupiter because Jupiter is going to pull down the object like anything. Okay, and of course by now you know, right? It's difficult to jump on Jupiter, right? Because Jupiter is going to pull you like down like anything. Okay, so obviously the value of escape speed from Jupiter will be different. Later I'll show you the share you with the values of also. Okay, but for the time being, do you agree with me right now if I just bring Moon now? Okay, Moon. If I want the object, okay, to escape from moon, so we need to have some minimum velocity, right? So that the object escapes from moon, right? What do you think is going to happen now? Will the escape speed in moon, okay, will it be larger or much smaller now compared to Earth, of course?
Smaller, sir.
Smaller. And the reason is very simple. Mass of the moon is very, very small compared to Earth. So moon is going to pull down anything with a lesser force. Okay. So it is easy to escape from moon. Okay. And that's why let me just tell you something. See, do you get atmosphere in moon or not? Do you have any atmosphere in moon or not?
Yes, sir.
We have atmosphere in moon. Atmosphere means gases like oxygen, nitrogen, hydrogen, carbon dioxide, right? Do we get that or we do not get them?
So not concerned about oxygen, but some other gases are present. I know.
No, 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 not all. Means mostly some other gases means you know what we get wind of the sand in moon or I don't know what to call it. Okay, but you don't get gases actually. Who stays in moon like that? You do not get actually. You are thinking right? We get gases, all these gases, right? See, gases can be formed because of reactions, but they don't stay on the surface of moon like that, on the atmosphere of moon. They just escape. Now you guys tell me, okay? I'm telling you again, okay? You don't find these gases on the surface of moon. You do not get them. Okay, let me tell you why. Because what do you think? Is it easy for the gases to escape or difficult for the gases to escape? Gases, by the way, by now I think you know, gases are particles, right? Which have some velocity. No, in any room you keep gases, they fly here and there. Okay, so these gases in moon also, you know what? They find it very easy to escape from moon. Means they don't have to stay at moon, okay? Because gravity is very less in moon, right? What about Earth? We get atmosphere in Earth. Now you tell me, you can tell me, right? Why do we get gases in Earth? The reason is very simple. The gases on Earth, though they are moving, they do not move with a velocity of 11.2 kilometer per second. So they find it difficult to escape from Earth. That's why we still have gases on Earth, okay? Imagine the escape speed on Earth also becomes very, very small. If the escape speed on Earth becomes very, very small, you'll find all these gases will also escape very easily. They'll run away from Earth, okay? And then, of course, right? Okay, there'll be no atmosphere, okay? So basically, what I'm trying to say, if you want to have all these gases in a planet, right? What kind of escape speed you should have? You should have low escape speed or high escape speed. You don't want them to leave, right? The gases, right? In order to happen that, right, the escape speed should be how much? Very, very optimal, no? Around 11.2 per kilometer per second. Okay, so that should be the escape speed. And normally gases, they do not acquire this much escape speed because of in the atmosphere. That's why they're still going to be there in the atmosphere. Okay, so if somebody asks you why there is no atmosphere, or let's say why there are less gases also, if you want to talk like that, okay, why there are less gases in moon, your answer should be because moon has less value of what? Less value of escape speed. The gases, they find it very easy to escape from the surface of moon. That's why there's no atmosphere as such as Earth. Okay, I hope you got my point. And now let me tell you what are we going to do. Okay, we are going to write a formula finding what does escape speed depends upon. I already wrote a value, okay, but I have not shown you what does it depend upon, but we are going to do that. Okay, so the derivation is very difficult. That is what I was talking about. Though I've been talking slowly, I think you're getting me. But let's go into derivation. Okay, so we are going to calculate expression. Okay, so this is what we're going to do. And I checked the notes just now. Okay, I did not see this notes for escape speed, so I need to put it. Okay, escape speed is expression for escape speed. Okay, okay, I'm going to go slow, but let's do properly, huh? Okay, so see, give me just 1 second, 1 minute. Let me just find out this 1 minute, 1 minute. Okay, so let's start. Okay, so see, so I will start with Earth, okay, and then later on I'll show you how to apply this formula or expression for any planet. Okay, so let's start with Earth. This is our Earth. This is the center of the Earth. Mass of the Earth is me. Radius of the Earth. By now everybody is clear what we are doing, right? This is radius of the Earth. Okay, so right now we are saying the object which is present on the surface of the Earth. The object has mass how much? Mass of m. Okay, okay. Let's say we have thrown the object. with a velocity. I'm going to write the velocity with v. Okay. Right now, I'm not calling it escape speed, but let's say the velocity is v. Later, I'll tell you it is escape speed, or I can do it right now. So let's say it is escape speed. You already know if I throw this object with escape speed, it is going to go so far, and then finally, right? Okay, it's going to reach so far and so far, it will not be pulled back by the Earth again because the gravitational force is going to be zero. So far, no. Let's say the object has reached here. We call it infinity. You can understand. It's very far. I want to do that. Okay, and that's why you see if the object is reaching infinity, that means the velocity with which you are throwing the object is the escape speed. Otherwise, it would have not reached uh, infinity. Okay, so you can understand till here, I guess. Starts from here, reaches infinity. Okay, I am saying in between. Okay, in between, the object is going to pass from 2 points, means it's going to reach here and reach here. 2 points called A and B, which are very close. Okay, that means A and B are very close. I represent this by dx. If you are clear with dx, I can proceed. Are you clear what is dx? Or let me ask you, what is A? Are you clear? A, point A. Are you clear what is point A? Maybe it's not clear. Let me try again. I've thrown the object. The object is this one. When I throw the object, it starts from here. It goes, okay, away from Earth, away from Earth, away from Earth. After certain time, it reaches a point A. And let me tell you, when it reaches the point A, the distance between, okay, the distance between Earth and this point A, I'm going to call it small x. Okay, just x, okay. And is it infinite distance? No, not infinite distance. What is the meaning of not infinite distance? Not infinite distance means when the object has reached here, the distance is not infinite distance, it is some x value. That means the object is still attracted to Earth with some force. Okay, that means if the object is at point A, there's still some force not equal to zero. There's still some force, okay, not equal to zero between the Earth and the object. The force will become zero only when the object reaches infinity. Okay, so I'll just show you again very quickly. I hope you are getting me. The object was on the surface. I'm sending the object from the surface. I'm throwing it. So once I throw it, it's going. Okay, reaching a point A. When it reaches the point A, the distance between the object and the planet Earth, it is x. It is not infinite distance. There's still some force. After reaching A, it reaches a very small distance. Later, it will reach another point called B. Then it is going to go on, and so keeps on going and reaches finally to this point called infinity. Okay, are you getting me? What is point A? If you're clear with point A, I think I can proceed. I hope you're getting me what we are doing here. Okay, see, I told you it's a difficult one, so I'm going slow. So but I need your response right now. Okay, guys, are you clear with point A? Are you clear with point A? If it's yes, you say yes. Okay, Dasanbhai is saying yes. Speak, guys. I want to hear you also. I should ask you to on your camera also. I want to see you also actually.
Yes, sir.
Okay, Sapnik is clear. One, two more responses, guys. Hurry up, then I will proceed. Sneha is fine with that. Fiona is there. Ryan is there. Arisha is there.
Yes, sir.
Okay. Pragya, are you getting me what I'm doing, Pragya, this time?
Yes, sir.
Okay. What about your exam, Pragya? I forgot to ask you. How was your exam?
Sir, it was fine.
It was fine. Okay. Okay, then who else is there? Who wants to talk? Anything? Okay, fine. I think you have no problem. So I'll proceed. Okay, now say. Let's quickly find the force between. Okay, I'm writing here. Force between, okay, the mass m and the Earth when the mass m, okay, mass m is at point A. Okay, is at point A. Let's do that. Okay, I already told you x is the distance. By the way, let me just tell you, okay, this A point is any general point also. It can be anywhere. If I tell you x is, okay, 1,000 meters, that means I'm talking about 1,000 meters away from Earth. If I tell you x is 2,000 meters away from Earth, or 2,000 kilometers, okay, that means I can talk about any, okay, any point A. which is at any distance x. Okay, so x is general here right now. Okay. Okay, now see. So I'm going to write the force between this mass m and the earth if the mass is not on the surface. Okay, if the mass is here. So let's do that. The formula is very simple. The formula will be F equals to how much? Capital G, mass of the earth, mass of this object m divided by distance between them squared, right? The distance right now you can check. The distance is xe. Oh, sorry, not xe but x squared. No, so I'm writing like that. I think everybody's clear with this. Okay, so I'm not going to ask you. If you have doubts, you can stop me, huh? So I'm just going to proceed now. See. Okay. So what does this force do? Let me tell you. This force is going to pull back, try to pull back. It may not uh, win in pulling back the object, but no matter the object is going to experience a force called F right now, and the object is going to be pulled towards the earth. Okay, that happens throughout this motion, right? The object is here, 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 right? And everywhere, okay, the object will still be pulled back by earth, but it will not come back because we are throwing with such a velocity. It still escapes, but at different points there's a force. Okay, now I'm going to ask you a question. Okay, say, give me an answer if you're okay. Let's say the object, it is present at A, but let's say it still goes to a point B. I'm telling you, okay, the object, okay, the mass m still goes from where to where? It is pulled by earth, but it still goes from A to B. Okay, my question is my question is uh, do you think we have to do some work or not to shift the object from A to B? That is my question. Think about this and give me an answer. Okay, quickly guys, quickly. Yes, object is still going
Yes,
from
sir.
A
We
to,
can do some small work.
yeah, yeah, object is still going very good. The object is still going from A to B. The work that we have to do is going to be a very small amount of work because the displacement itself is very small. Okay, so we'll do a lot small amount of work if the mass is still going from A to B. And why am I saying we have to do work? Because gravity still wants to pull it down, so definitely there's some work spent, there's some energy spent in taking the object from A to B. Okay, so I'm going to write like that, and my formula for work done will be force into displacement. Okay, so I am going to write the force F because that's the force against which we are going to do the work, and I'm going to write dx. Are you clear with this? If you're clear with this, I can proceed. I'm going step by step and slowly. Okay, if the object is going from A to B, we have to do work,
Yes,
small
sir.
amount of work, dw equals to f dx. Okay, if you're okay, I'm going to proceed. Guys, yes, one
Yes, sir.
response at least. Okay, okay, fine. So since others are not asking anything, so I'll proceed. Okay. Okay. Okay, now say, suppose now I write, okay, uh, work done, just check. Okay, that's pressure cooker. Okay. Work done to work done to send the object. Okay, to send the object, let's say mass m from surface to infinity. This is what we are going to calculate next. Okay, so just try to understand this. I told you it's a difficult topic, but it's a very nice method. Okay, so I'm just going to take up some time and then ask you again. Do you understand what is this? Work done to send the object from the surface of the earth till infinity. This is what I want to calculate. Okay, I'm repeating again. I don't want to calculate the work done to from A to B. I know that already, right? This is what I have to do. But I want to calculate the work done to take the object from here and make it reach here. What do you think? It's going to be a work done, a very large amount of work done.
Very large amount, sir.
Very large amount of work done. We have to do a lot of work in shifting the object from the surface till we reach infinity. Okay, let me show you a method how we are going to do that. See, I'm doing the same thing, don't worry, I'm doing the same thing. Okay, check. Okay, uh, You must be saying, why not use W equals to force into displacement, right? You must be saying that, okay? You will tell me, okay, let's write work done, the total work done to shift from here to here, surface till infinity. Write down the force and write down the displacement, right? You calculate what is the displacement and then you get the total work done, okay? Let me tell you, you cannot use this. I'll show you the reason. You cannot use this. Anybody knows why we cannot use this? Anybody who can tell me why we cannot use this?
So displacement is infinite, sir.
That is not exactly the reason. Something else, something else. Think, you might get the answer.
Negative work.
Yes, yes, yes. Siddharth was saying something, try again. Sorry, Siddharth.
Negative work.
Negative work. No, no, not because of negative work. Think again. Anybody who can give me an answer, I'll be very happy. Think more. You're trying nice. Okay, try more. I cannot use this formula. Force into displacement. Okay, let me tell you why we cannot do that. Okay, I simply cannot use F equals to F and then displacement. Okay, I cannot take the total force and displacement because the reason is very simple. This force is not a constant. Do you agree with me on this? Check. Okay. Force into displacement I can only use directly, right? Like that, provided your force is constant. But look at our problem here. See, I want to calculate the total work done. I'm going to start the object from here. I know what is the force because this is the center of the earth. This is the radius of the earth. The force is simply how much? Force, if the object is here, okay, force is capital G, mass of the earth, mass of the object by distance between them, which is RE square. So this is the force. But imagine the object is here now. Then the then the force between earth and the object will not be this much because the distance is changing at different positions, right? If I keep on changing the position, check, it's like going from away and away and away, right? What do you think, the force remains constant or doesn't remain constant? The force does not remain constant, so you cannot simply use F equals to F into D. You cannot use that because your force is not a constant. That's why we are going to use this method now, okay? And just check if you're okay or not, then we will proceed. See, just check, okay? Maybe you got some ideas now. I think you will get all the idea. But see, okay, at the beginning I told you it's going to be difficult because class 11, okay, you are starting, okay, and these topics are actually difficult, okay, to understand at the beginning, huh? So see, let's try still, okay, see. So how will I calculate how much work is done to reach till here? No, see, I'll do this method. See, I will calculate how much work is done. Okay, let me just ask you. If I tell you this is point P, some point P, and there's another point Q, very close, very close, just like A and B, right? This P and Q are very close, okay? So if I'm taking the object from P and Q, I'm repeating again, I'm taking the object from P and Q, the distance between P and Q will be very tiny, right? The distance will be dx, very tiny distance. What is the force between the object and the earth? When the object is at point P, you're going to say it is F, right? The force between object and the earth when the object is at point P. Okay, let me ask you, what is the force when the object is at point P? Is it same or almost same? That is my question. Between point P and Q, the force. The object is at point P, okay, fine. The object will reach point Q, okay, fine. Okay, the point P and the Q are very close. If I tell you the force between the object and the earth when the object is at point P is F, what will happen if the object is at point Q? What will be the force? Are these two forces going to be different or almost same? Can I take them same? Yes or no?
Yes, sir.
Did you understand what I said just now? This point P and Q are so close that I can say, yeah, between this point P and Q, I can say between the point P and Q, your F is constant or same, right? Between only point P and Q, because they're very close, I can say they're almost same. The value of force here and the value of force there will be almost same because these two are not very far apart points. These are very close points. Okay. Now you tell me, can I find the work done or not? What will be the formula? Yes, waiting, guys. waiting to take the object from P to Q. Okay, P to Q. Formula will be take the force multiply with displacement. Now, if I ask you, right, but this formula force into displacement you can only use if our force is constant, and that is what is happening right now between the point P and Q. The force F can be taken almost constant, so I'm quite okay to use that. Okay, so I'm going to write dW is equal to, see how am I writing the force also. Okay, I'm going to write the force as capital G, mass of the earth, mass of the object by distance between them, that is RE. So I'm writing RE square, and then I can write dx, no problem with that. This is quite all right. Okay, still our problem has not been solved. Okay, because we have found the work done only to go from P to Q. Okay, let's extend this formula now. See, let's try to go from Q to R. This is another point now, R. Okay, very close to Q, very close, almost close, or let's say very close. Okay, if I ask you now, are we sending the object from Q to R? Yes, we are doing that. We are sending the object from Q to R. Okay, how much work has to be done to send from P to Q? Work, I'm calling it dW1. Let's just call it dW1. Okay, I'm writing that force of 1. If I'm trying to send the object from Q to R, again I can use this formula. See, work done dW2 is equal to how much? F2 dx. Right now, let's say this is the force between here and here. No, some approximate force value between these 2 points. Okay, which I can take constant. So again, I can use this as dW2. Like this, you know what? I'm going to slowly take again another point, very close, very close, very close. Keep on shifting by little amounts, right? So as I reach here, right, I will have not only dW1, but I will have lots of dWs, dW3, dW4, dW5, dW6, right? Then I'm just talking about going from here to here to here to here to here, but slowly in steps. Okay. Now, if I ask you, what is the total work done? Okay, I'm going to say total work done must be equal to take the small work done to take from P to Q plus small work done to take from Q to R plus small work done to take from R to S and so on, right? If I add all of this work done, I'm going to get the total work done. I hope you got me what I'm trying to say, because that is what I want to calculate. See, work done to take the mass from where to where? From surface till we reach infinity. And for that, I simply have to add all this small work done that I've calculated. Are you okay till here? If you're okay till here, then I will proceed.
Okay, sir.
Okay, Samu is okay. What about others? One or two response quickly, guys. Arisha is here. Arisha, are you getting me?
Yes, sir.
Yes, sir.
Okay. I've made it look complicated, okay? But then I'll show you there's an easy way out. See, but of course, right? Calculating like this is not so wise. But don't worry, we have a method, and that method is calculus. I can still find total work done without doing all these things. By doing this also I will get, but this is a shortcut now. I'll show you the shortcut now. See, okay? See, what am I doing now? How am I going to do that? See, if you remember, taking the object from A to B is like taking the object from any general point A to any point B. Because point A is basically represented by your X, right? If I tell you X is RE, you are here. If I tell you X is more than RE, you are somewhere here. If I tell you X is more than RE, very much more, you are somewhere here, right? X is representing where are you, okay? So now check, see. Don't worry about this, now you'll get me. So I'm writing again this, dW equals to F dx. You know what is this? This is the amount of work done to take the object from A to B by a very small displacement, okay? Our method is this, see. I'm going to use this integration symbol. Integration symbol is looks like a snake, okay? So what I write here, I call it lower limit. What I write here, I will call it upper limit. Here also similarly, whatever I write is called lower limit. Whatever I write here will be called upper limit. Don't worry, you'll get me. Just give me some time, okay? Now check. What am I going to receive? I'm saying that integration means, okay, integration simply represents to add up. Not easy to get directly, okay? It's not the simple addition. Later you'll see that it becomes complex. But right now, for the time being, I'm saying it is nothing but adding up small things, okay? Adding up small things. Right now, you have already agreed. If I add all the small work done right from the surface of the earth, I'm repeating again. If I start adding up, okay, this integration dW means I want to add up all the small work done right from the surface till we reach infinite distance, if I add up, right, then that is going to give me total work done. So I can call it total work done. Total work done, okay, work. Are you clear? That's the meaning of integration. That means, okay, if I write integration of dx, it simply means I'm trying to add all the small displacements, right from point A, which is the lower limit, till we reach our point B, which becomes the final point, no? Okay, initial point to final. I'll add all the dx that I can get throughout. Okay, I keep on adding that. I get the total displacement that way, right? That is what we can do. Okay, I hope you got me what's the meaning of integration, right? Integration means keep on adding the small parts till you get the whole big part. Okay, so right now if I ask you, are you clear with the meaning of integration symbol on the left hand side? Does it represent work now or small work done, or it represents total work done? I'm asking you this part. The moment I write like that, I'm trying to tell you it means
Total work done, sir.
total work done. That's it. That means I'm going to add all the work done right from the surface till we reach this point. Keep on adding all the small work done. DW, 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 like keep on adding them. Okay. So I think you got me a little bit of it at least. At least, guys. Is it okay? Are you comfortable?
Yes, sir.
Okay. Okay. Then I'll proceed. Okay, guys. Now, any problem? Please stop me. Huh? Okay. Now see. Okay. Now, if I integrate the left hand side of this formula that I have already written for general, right? Any point. If I integrate, if I add up all the small work done, that means I have to add up all the f dx. Okay, so that is the meaning on the right hand side. If I want to find the total work done, I have to find all the f dx that I have throughout the path. F dx right from the surface till we reach that point. Okay. Now let me show you what will happen here right now. Okay, it's a very nice way to write now. Just check. Uh, what are we adding here? Let me be clear. We are adding here not dx. We are not adding, keeping on adding dx and dx and dx and dx. No, we are not adding dx. Let me tell you what are we adding. We're adding the product of, let me just show you here back. F dx here, then the product of f dx here, then the product of f dx here. Okay, this is the product of f dx, f dx, f dx. We want to add all these f dx, f dx, f dx, and as I keep on going away and away, right? Your f is not a constant. Please remember that, right? Your f is not a constant. F is changing. And how is f changing? Let me just write down that also and tell me whether you're clear or not. Okay, see, I can write integration of dw equal to integration of f, right? See how am I writing? Capital G, mass of the earth, mass of the object divided by distance between the object and the earth, right? And I told you the distance between the earth and the object, generally I'm taking the distance to be x right now. So I'm writing x square. Then I have dx. Because if you remember, that is how I've written the force also. Check. This is at any point such as A. Okay, this is your any point. Let me show you how this is useful for us. Okay, see, just now I told you, right? The force is keeping on changing. If I keep on going away and away and away, your x keeps on decreasing. So this formula right now is keeping a track of how the force will change. If your x is increasing, your force is decreasing, right? So you keep a track of the value of force also. Okay. Let me not speak like that. No problem with that. But let me say I've just replaced the value of x. Oh, sorry, f. Okay, which is definitely not a constant because you're reaching from surface to this point. Okay, a little bit I think is clear from infinity, right? Okay, so let me just talk about that now. Okay, now see, let's say we are on the surface, no? Okay, now see, okay. So what are the meaning of lower limits and upper limits? Let me just talk about that very quickly. So let's just check. Okay, see, I told you right now we want to start from surface. Starting from surface, this means initial, right? So this is our lower limit. So if I am talking about the surface, the value of x will be equal to exactly equal to RE. I think you are getting me, right? Check, all of you. It means I'm talking about point somewhere here. Wherever the object is, right, that point I'm calling it A. Okay, so right now if I'm starting from surface, that means our point A is somewhere here. That means this is the x, right, the distance between the center and the surface. That is simply RE. Okay, because of which, see, I'm going to write over here RE. Let me tell you what does it mean again in the formula. Okay, check. It simply means I'm going to displace the object starting from the value of x, which is equal to RE, which means you are on the surface. I'm going to repeat it again, okay? This RE, when I write here, it simply means we are going to start displacing the object and we will displace it, okay? By how much amount? By dx amount, no problem, okay? But we will start from the surface. That means the value of x should be equal to RE. That means we are starting from surface. The value of x is how much? X is RE. That is where we are going to start with, okay? And where we are going to stop, let's keep on adding dx, 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 and when we reach here, right? Automatically you reach here. That means the distance between the object and the earth is going to be infinite. So x will become infinite. So I'm writing here infinite here. That means that is where I'm going to stop. Are you clear what is this and lower limit and upper limit? Lower limit and upper limit are not the values of force. Please remember that. This lower limit and upper limit are the values of this small thing that you're trying to add up, no? Dx. Okay, that means x. Starting from the surface where the value of x is Re, you stop when you reach the value of x becomes infinite. That means you have reached infinite distance, okay? This is not infinity right now. This is infinite distance, we call it. There's a difference, okay? Infinite represents a value. Infinity represents a very far point, no? Infinite represents a very big value, okay? Guys, let me just quickly ask you, are you clear what I did just now? Or let me just write again and then let's talk quickly, okay? See, I told you I'm going to go slow, but I'll try to make sure you understand. This represents a small amount of work done when I'm taking the object from any point like your A to any close point B by a small displacement dx against the force of gravity, right? Against the force of gravity, where A is at a distance of x from the center, no? So force formula also we have written, okay? Then I simply have written dw equals to capital G, mass of the earth, mass of the object by x square. That is a general formula. I can apply this anywhere I want. Not here necessary. I can apply here also, anywhere. Okay, because x gives us the freedom, right? Because x can take any value. Okay, I can apply this and I get it anywhere, right? But the moment I put it an integration symbol like this on both sides, it simply means I want to find the total work done. Okay, that means I want to add up all the small work done. Okay, starting from where? Starting from a position where the value of x is Re, that means from the surface till we reach infinite distance. Okay, now let me go to the left hand side and then explain to you what is going on. See, left hand side represents now, if you are starting from the surface, your work done must be zero. Why zero? Because when you just start here, right? When you just start from here, you have no displacement, so total work done here should be equal to how much? Zero. So we are going to start with a zero value of work done. Right now, if I tell you, let's throw some object from your room, no? Okay. That means you're starting when the object is at the room, right? Already the amount of work done is zero, right? Because you have not done to keep the object in the room right now. Okay, let me just speak like that. But once I throw it up, then you start calculating the work done, no? Because we're talking about from surface onwards. Okay. So right now, anything lying on your table or anything, right? The amount of work done by you is zero right now. Okay. Then we start throwing it up. So we start with zero value of work done, and then finally when the object reaches infinite distance, right, we say we have done some quite a good amount of work done, and let's call it capital W. So this is the total amount of work done. Okay, are you clear, guys? What am I doing? Is it okay? Because I told you it's difficult, I'm going to go slow. If you're clear with this, then I can proceed.
Yes,
Okay, let me
sir.
just okay, let me ask you, are you clear with this? Dw equals to fdx. Anybody who wants to just talk quickly about this one, guys? Don't worry, we are almost done. Okay, we're almost done. If you have understood the hard part, is fine. Are you clear? What is this? Anybody who wants to explain this very quickly, guys? Come on, come on. Sit
Amount
down.
of
Yes,
work
try,
done.
try. Very good. Amount of work done. Small amount of work done. Small amount of work done. Okay, Sanu. Yes, continue. Yes, yes. I'm waiting.
The amount of work done to move a body from
Okay,
a
from
point to another.
one point to another point or very close point. I'm asking you
Very
this.
close.
Very close point. Okay, but everything you have not mentioned. I want to listen more. Yes. Anybody who wants to add up, some detail is missing. Some detail. I told you today I'm going to do only this topic, but I'm going to talk slowly and in detail. Okay. So you also have to talk in detail now. Anybody? Because I know some of you are missing the detail here. Is this simply the small amount of work done in displacing by a small displacement, Or we also have to mention against the force of gravity. We have to mention that, right? It is against the force of gravity. And between those two very close points, I can take the F constant. That's why I can apply work done is equal to force into displacement. And that is what we have done right now. Okay, I think you got my point. I think everybody's okay with the detail that I just brought in. Okay, that means you have to mention this is the amount of work done against the force of gravity, because of which I can write like this. Because of that F, no, we can write like that. Only if you mention we are doing work against gravity, obviously, right? This is pulled down, I'm sending it up, I have to do work against gravity, so okay, I think you got my point. Let's be clear with this, guys. Yeah, Sanu can try, or any other one, any student can try again. What is this? What is the left hand side and what is right hand side? You have to tell me what is left hand side. First, you tell me what is left hand side. What does it mean? Or let
Total
me
amount
ask
of
you.
work done from moving a
Okay, very good, very good. Total amount of work done in moving a particle from where to where? You can look at the right hand side also now. From where to where?
from this Earth surface to infinity.
Okay, from Earth's surface to infinity. Yes, from Earth's surface
Against
to
gravity.
infinity. Very good. Okay. Uh, when? How do I know we are talking about the surface of the Earth? Because when we are at the surface of Earth, the value of x becomes re. That's how we put the values. Okay. Slowly, slowly. Don't worry. You are going to get what is going on. Okay. And then we are going to stop in a position where the value of x becomes infinite. That means we have reached infinity, and this is what we are going to calculate, guys. Okay. Okay, now let me just bring to you some formulas, and I think we should be fine. So I'm just going to proceed from here. Okay, if you guys have question, you can ask me. Okay, now check. The formulas are like this. The first formula is very simple. If I have integration of anything, okay, let's not be w. If I have integration of m, it means I'm trying to add up a quantity which is very small, that is m, and this is a very small part, right? That is your dm. This is dm. If I keep on adding, right? If I keep on adding dm, I'm going to get the total m, right? So I'm going to get m, okay? So integration of dm simply means that you are going to get a quantity called m. Please remember that. Add up small m, you get the total big m, no? The total value, okay? I'm writing like that. But if I have limits like m1 and m2, it means that, see, let me show you what is the meaning of that, see. It means you're adding the dm, right? Okay, fine. You're adding dm, but you're not starting from all the values of m. You're starting from this value, which is m1, and you're going to stop at m2. Now you're adding dm, see, dm, and you stop here. That means you want the integration, you want the addition, right? You want the addition of dm, right, from m1 till m2. No, this is what you want to calculate. Total between m1 and m2. Those are called limits, okay? See how am I going to use them right now? When I integrate it, I told you have to use this formula. Then let me show you how to put the limits. You have to put here a bar like that as a symbol again. You have to put m1 lower limit. You have to put m2, which is the upper limit. Then you have to start substituting the values, okay? In place of this m, first you are going to put the upper limit. It's going to look like m2. Then when I put the lower limit, you have to put a minus sign. Then you're going to put the lower limit, m1. Okay, so this is how you're going to do with this, okay? Later I can give you a note on this, how to apply the formulas. But for the time being, I think you got me. Let me show you another formula now. See, if I have a formula, integration of m dm, integration from the limit m1 to m2. This means I'm trying to add not only dm, but the product of m and dm. I want to add them, okay? Starting from some point to some point, I want to keep on adding them. So see what will be the formula. I'm telling you, this is done in class 12. So in detail, actually, you're going to study that time, okay? But for the time being, let me just proceed with this. Okay, check now, okay? If you have a formula which looks like mdm, the answer will be the same. You write m, you increase the power by 1, and you write 2 here, and you divide by the increased power. I'll write the general formula, just give me some time. Of course, you have to write the limits from where to where, from m1 to m2. This will become like this, say. I'm going to put this upper limit here, then I'm going to put the lower limit. When I put the upper limit, it's going to look like this. m2 square by 2 minus m1 square by 2. Don't worry, if you did not get me, you'll get the next one. m1, m2. If I have m square dm, if I want to integrate this kind of quantity, okay, I have to do this. See, sorry, I have to write like this. I have to write take the power of m and increase by 1. So power will become 3 now and divide by the increased power. Again the limits m1 and m2. So the answer will become m2 to the power cube by 3 minus m1 to the power cube by 3. Okay, so don't worry, you are getting me. And next, if I ask you m to the power 4 dm, suppose integration from m1 to m2, your answer will be how much? I think you can guess now. If you have m to the power 4, right, already inside the integration, the answer for this will be m to the power 5 by 5. See, I cannot derive all this, okay? It's a very big topic to derive, okay? But I'm just can tell you how to apply them. That's what I'm doing right now, okay? So see, the power is 4, right? The power here will become 5. And you have to divide by the increased power. And again, we are going to put the limits as m1 and m2, okay? So let me just show you how it's going to look like. m2 to the power 5 by 5 minus m1 to the power 5 by 5, okay? Let me write the general formula now, see. If I have x to the power n dx, integration from some integration from x1 to x2, the answer you can understand now. You have to write x, you have to write the power and you have to increase by 1 and you have to divide by the increased power. That is your n plus 1. And of course the limit will be x1 to x2. Okay, this one I'm not writing right now everything, but I think you got me till, if you got me till here, you can tell me. If you still have confusion, you can ask me, guys. Are you okay how to integrate? Mm, at least you understood. You do not know the full meaning till now, maybe. Let me just say like that, okay? It's quite okay not to know everything about integration. At least you should know right now how to apply this formula at the moment. If you understand this much, how to apply, we are good. We are good. Let me say like that. So can you apply, guys? That's it.
Yes, sir.
I've replaced the m by x, okay? What about others? I'm waiting, huh? You're not responding. At least you should say yes right now. If you're okay.
Yes,
Waiting. Okay, Dasama
Yes,
is
sir.
okay. Arisha is okay. At least to apply. Forget about other things. At least to apply. I told you, you are going to become more intelligent maybe next year. Okay, this year you're not going to be so intelligent. Okay, that's how you this year is. Okay, class 11 is like that. Okay, so let's apply this now. Okay, I'll give you one more situation. Let's apply. Okay, see, I have integration 1 divided by x to the power square and dx. Okay, I will write here integration x to the power minus 2 dx. We can do that because when I bring it up, right, it's going to look x to the power minus dx. It's minus 2, I mean to say. So let's apply now the formula. It's going to look like this. Say, you have to write the power. Yes. You have to increase the power by 1 plus 1. Then you have to divide by the increased power, whatever is the increased power is. Okay, so this is the increased power. See, did you understand what I did just now? Check. I've applied the same formula but I taught you just.
Yes, sir.
Okay, so Sanu is okay with this one. What about Arisha? Fiona, then Cordon is also here.
Yes, sir.
Okay, what about
yes,
Cordon?
sir.
Cordon, Sagnik is okay. Cordon.
Yes, sir.
Okay, Pragya is clear with this one. Just check. Just to apply. Forget about every other thing. Okay, the meaning and all. If you forget also right now, it's okay. Pragya. Yes, I'm waiting for you. Hmm. Pragya is not there. What about Siddhant? Is it making sense, Siddhant? Just check. Okay, Siddhant is saying yes. Okay, then I think I can proceed. Okay, so I'm going to use this. Okay, but let's arrange a bit properly so that I can use it. No, see, I'm going to write like this: x to the power minus 1. You'll agree with me because minus 2 and plus 1 is minus 1 divided by minus 1. Okay, now what I can do, uh, this minus sign I can just bring up here like that, so I don't have to write a minus sign down here. So I'm going to do that, and finally I'm going to write minus x to the power minus 1. Okay, this x to the power minus 1 I can simply write minus. Okay, minus is already there. 1 over x, right? Because if I write n to the power minus 1, it simply means inverse of n. X to the power minus x minus 1 means inverse of x. No? So I'm going to get this much, say. So I'm going to get minus 1 over x. Okay, so I'm going to use it directly, say. directly to this formula which has been waiting for us. Okay, you know what we are calculating, don't forget. So let's just do this now. So all of you are clever now. Okay, and if I ask you what's the integration of dw, you are going to simply say integration of dw is w, right? Integration of dx is how much? X. Integration of dw is how much? W. Okay, of course you have to put the limits. So I have to put the limits as lower limit and upper limit equals to. Okay, here let me tell you what are we not integrating. Okay, we are not adding up g, m. Okay, these are constants. Okay, so I'm just going to write them outside. See, g, m, e, m, those are constants. Okay, uh, as I take the object from surface till I reach infinity, the value of x is not a constant, it keeps on changing. So that's why I'm putting it inside the integration. It looks like 1 over x square dx, of course with the limit r e and then infinity. Okay, so I'm just writing that. Okay, now you can understand already the form is very simple. I have to integrate this, which I've shown you just now, how much we are going to get it. I've shown you just now, if you remember. And then on the left hand side, let's just put the values. Okay, I'm going to put this w here. I'm going to get w, yes, total work done, minus. When I put it over this one, lower limit, I have to put a minus sign, but this lower limit is 0. So in place of w, I'm putting 0. Okay, equals to capital G M E M, which is a constant, comes out just like a differentiation. Constants, they are going to just come out. Integration of this, if you remember, I am getting minus 1 over x, which I showed you just now. Limits, of course, from surface where the value of x is re and till we reach infinity where the value of x is infinite. Okay, so this is not infinity. Okay, this is infinite. Okay, guys, are you clear till here? After that, it's very simple. Okay, okay, now I'll not ask you. If you have doubts, you ask me. Okay, so let's proceed. W minus 0 is w, so I'm writing w equals to capital G M E M. This minus sign I can just write outside. Okay, here somewhere here I'm doing that, and then I'm just going to get 1 by x. Okay, and of course the limits are r e and then infinite. Okay, so I'm just doing that. The minus sign I'm just taking it outside. Okay, because this is a product actually. Okay, if you have doubts, you can feel free to ask. W equals to minus g again, m e m. I'm going to start putting the limits now. Okay, so you decide and you tell me what's going to happen. So the upper limit is infinite. In place of x, I'm going to write infinite. So I'm going to write here 1 by infinite. When I put the lower limit, I told you I have to write a minus sign. I'm going to write 1 by, in place of x, I'm going to put now re, 1 by re. Okay, in place of 1 by x, I wrote 1 by re. In place of 1 by x, I wrote 1 by infinite. Okay. Now all of you know, right? 1 by infinite. 1 by infinite means 1 divided by very, very large number is going to be almost equal to 0. So I'm writing here tending to 0. This part is negligible. This part is 0. Almost equal to 0. Okay. So I'm going to get w is equal to minus of capital G M E M. Then I'm going to get minus 1 by re. No? This is what I'm going to get. Of course, you have to multiply these two things. So minus and minus will become plus. And the work done, I'm simply going to get is work done equals to capital G mass of the earth. Then I'm going to get mass of the object divided by re. Guys, if you're okay with this, then we are doing fine. We just calculated something. If you remember, we calculate the total work done. Let me tell you what is this. If you're forgotten, okay. Now you'll get me, I think. Total work done by a method of integration, okay. In taking the object m from the surface till we make this object reach where? Infinite distance, or let's say infinity. And we have got this formula. Very nice formula, okay. Very simple formula actually, check. We don't have infinity in this formula, nothing, right? Like that, but we got it, okay. Guys, are you clear at least till here? If you're okay till here, then we are okay. Next step is very simple. That means we really have to do work, right? Yes, we have to do
Okay,
work.
sir.
Okay, so we have this object here and we really want to send it till infinity, right? So the question is, do we have to do work? Yes, we have to do work. How much? Equal to capital G mass of the earth, mass of the object that we are sending divided by just the radius of the earth. In sending the object from surface till infinity, we have to do this much amount of work. I hope you understand till here. At this point, you may be totally lost. Okay, what is going on and what are we doing? Don't worry. Let me tell you what are we doing. We're calculating what must be the velocity with which I must send this object. No, that is what we're calculating. Escape velocity so that it reaches infinite distance. Okay. Okay, I'm just going to go to the last part now. I hope you're clear what we have done just now. This is the total work done we have calculated. Okay, now says, if this much work has to be done on this object, I'm repeating again. If this much work has to be done on this object, I'm repeating one more time. If this much work has to be done on the object, this object is going to gain energy, right? Example, I take a ball, I kick this ball, okay, kick. Did I do work on the ball? Yes, I have done work on the ball, right? I have kicked it, no? Kicking is like pushing, right? Pushing the ball and displacing the ball means displacement, no? See? Okay, kicking the ball means pushing. When I kick the ball, it undergoes displacement. That means there is force and displacement. That means we are doing work, no? So we are doing work means we're kicking the ball means we are doing work, okay? Let me say I have kicked the ball, I have done a work of 10 joules. So I've kicked the ball and I've done a work of 10 joules by applying some force and producing some displacement. Okay. My question to you is this. Do you agree with me that the ball gains kinetic energy or not? Simple question. We are doing work on the ball. How much work are we doing on the ball? 10 joules of work we are doing on the ball. What is the ball going to do? Is just going to sit or is going to gain kinetic energy? It's gaining kinetic energy. So if I ask you, how much kinetic energy is gained by the ball? What is your answer? Anybody who can tell me this has some ideas. Guys, let me just take 2-3 minutes more. Maybe I can do some other time. Okay, complete it later also. But I just want to complete right now. Okay. Otherwise, for next day is going to be very difficult. Okay, guys, let's complete today only. Okay, guys. So, what is the kinetic energy of the ball? Who can answer?
So half mv square.
Half mv square. Okay, half mv square. You're right. That is the formula. That is not wrong. Okay. But I wanted to know a number here. You should have told me, you know how much? You should have told me 10 joules. I'll tell you the reason why, guys. Okay, see. This is a ball. We are doing a work. I am doing a work. Let's say it's me, okay? When I do a work of 10 joules, guys, you tell me, how much energy am I losing? Yes. If I'm doing a work of 10 joules, how much energy I am losing? Energy lost by me. 10 joules, right? Obviously, you cannot say no to this, okay? I know this much you understand, everybody. If you do a work of 100 joules, you will lose 10 joules, 100 joules of energy. Okay. Who is gaining this energy? This ball, right? It is in the form of kinetic energy, no problem, but it is gaining. It is going to gain 10 joules of energy because energy lost, I don't know if you have heard or not, energy loss is always equal to how much? Energy gained. If I am losing 10 joules, there must be objects around me, those are gaining 10 joules of energy. That means 10 joules of energy lost simply means 10 joules of energy gained. Let's come back now, okay? Do you agree with me that we're sending this rocket, let's say this rocket, okay? We're sending it away, this object. So we have to do work. If we do work on this object, do you agree with me that this object will gain kinetic energy or not? We are kicking it. You can imagine like kicking also. Okay. So I'm going to write now, okay? How much will be the kinetic energy of this object? How much work are we
Equal
doing
to
on
work done,
the
sir.
equal to work done. We are doing a work of capital G M E M by R. E, of course. Okay. So this is the amount of work done. And whatever amount of work we do on the object to take it from here to here, that is going to appear as kinetic energy of this object because energy lost by us in doing work is energy gained by this object. Okay. Check now. This is the last step. How do you write kinetic energy? Somebody told me, right? Okay. Half mv square. All of you agree with this, right? Check. Earth is not moving, okay? The object is moving. So I'm writing a mass of the object. Kinetic energy of the object means I have to write here mass of the object, okay? You cannot write mass of the Earth, no? Okay, now see. Last part is this. I have to write a E here. Let me tell you why. Because whatever is the amount of work done is sufficient for the object to reach to infinite distance. And if the object is reaching to infinite distance, that means the velocity of the object, it is a very special velocity which we call it escape velocity, right? Then only with this much work done it will reach from surface to the infinite distance. Okay, are you clear that I'm substituting the velocity to not only any velocity, it is a very specific velocity which is escape velocity, with which, okay, or which is gained by the object when this much amount of work is done in shifting the object from surface till infinity. Okay, so this velocity, I'm being very specific now, it is not just any velocity, it is your escape velocity. And this is how you are going to get your escape velocity formula. See, I'm going to cancel the m. I'm going to transfer the 2 on the other side. I'm going to write ve is equal to twice of capital G m e, then of course divided by re. So I'm going to get ve square actually. Then simply I'm going to write here ve escape velocity equals to root, okay, everything root twice of G m e divided by re. Are you getting me? So this is how you are going to calculate your escape velocity. One more change I can make it. In place of GME, everybody knows today, I think, right? We can write GRE square, right? Because let me show you again. G is equal to how much? Capital G M E by RE square, no? So I can use this, okay? So let's guys finish today right now only. Let me just put it back here. So escape velocity will be equal to root over of, in place of GME, I told you I'm going to write GRE square. So GRE square with a 2 here and divided by RE, okay? RE, this RE gets cancelled. I'm simply going to get root over of twice GRE. If I put the values now, I'm going to get like this. See, twice into 9.8, which is the acceleration due to gravity on the surface of the Earth. That's what I've done. Radius of the Earth is 6,400 kilometers. That is into 10 to the power 3 meters. When I do this calculation and convert into kilometer per second, I'm going to get exactly how much I told you before, 11.2 kilometers per second. Okay. But anyways, this is how we are going to do it. Okay, guys, our main aim was to understand integration right now here. Okay, can I say it is okay, or is it difficult, or at least some part is clear? Like, is it okay? Can I stop, guys, now right now?
Yes, sir.
Yes,
Okay,
sir.
right. Fine. Okay, okay. Any doubts? Anybody who has doubts, you can stay back. Still ask me. Okay, at least little
No, sir.
comfortable
No
you are.
doubts.
I feel. I think you are at least little comfortable, right?
Yes, sir.
Yes,
Okay.
sir.
Okay, okay. See, everything may not be clear. Okay, that is the whole point here right now, because you don't know integration till now, no? So commonly, right? Common sense, right? How can everything be clear when we don't know much about integration? Okay, I tried my best right now for class 11 level. Okay, I'll not speak much. I'll stop for right now. Maybe by tomorrow daytime, I'll give you this notes for this one. Okay, so I just want to stop, guys. Okay, tired, huh? So I'll meet you next day, huh, guys? Bye, bye, huh? Bye, 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 bye,
Bye, sir.
bye,
Thank you,
bye,
Sir.
sir.
Okay,
bye,
sir.
bye, bye, bye.